Okay, I think I'll get us started. Um, Thank you very much for showing up in such force. This is very humbling for us. Thank you. Um, Over the next months, we'll be organizing this seminar, and it'll take place every second week. I'll take off these headphones because there's still people entering, and the ringing is disturbing me. So I'm not ignoring anything you're about to say. I will just protect my ears a little bit. Okay, so yes, over the coming months, we'll be organizing the seminar. It'll happen every 2 weeks, and the timing will change depending on where the speaker is based. Because for people in Asia, they will not be able to speak, at 4 a.m. And so, if we have a speaker from the Asia Pacific or a speaker from Europe who would prefer things on the earlier side, it'll happen at 9 a.m. At Greenwich Mean Time, and otherwise it'll happen at 2 p.m. There will be 3 chapters in this first season, if you like, of the seminar. So the first chapter is one that I'll introduce today, and it revolves around generalized base, and I'll sort of introduce the speakers and coordinate it. The second chapter revolves around resampling-based, and martingale posteriors, and Edwin, who I've seen is here today, and whose jolly face you can see on the slide as well, is leading that chapter. And the third chapter, for which we haven't set exact dates yet, but it will happen after the summer break, will revolve around PAC-Bayes. So a lot of the heavy mathematical machinery that we'll be dealing with implicitly throughout the series will be covered then. And Pierre has volunteered to lead that. So while Edwin, Pierre, and I are leading the scientific component, I would be amiss if I were not mentioning Matthias and Jan, who've done a lot of hard legwork in putting this all together. They're 2 PhD students of mine who've really been instrumental in getting this off the ground. I've had the vague intention of doing this for a long time, and my ineptitude has prevented it from actually happening. So a lot of accolades should go to both of them, and I'm really grateful how amazing a job they've done in supporting this. And they're running the mailing list and everything. So thank you to both of you. As for how we're going to engage with the audience, so questions obviously welcomed and invited. Given the size of the attendance, it's probably unlikely, depending on how many questions there are, that yours will be asked. However, there's a Q&A function in Zoom that we'll be using to kind of figure out which questions we will be asking. So if you can't see the Q&A icon, by the way, you should click the More button, and then you can select it, and it'll pop up in your bar. When you ask a question, this Q&A function enables others to actually see your question and upvote it. So if your question rises all the way to the top, then congratulations. By the law of social media, your question will probably be asked. So Jan and Matthias will do the selection of questions, and they will do the monitoring of questions and interrupt me in speaking at appropriate times today, as well as the speakers in the next months as well. After the talk, we'll have the opportunity as well for people to ask questions, in person with their voice, which is obviously much nicer for all of us. And at that point, you'll raise your hands in Zoom. We'll probably remind you of that at the time. And again, Matthias and Jan will try to make things as fair as possible in that regard. Before I start with the actual scientific component today, I wanted to share this slide with you. If you find this useful, you can take a quick picture on your camera or whatever. This is kind of a rough overview of all the resources relating to the seminar and where you can find all the information you would want. If you weren't quick enough on your feet to pull out your phone and take a picture, don't worry. The slides will be uploaded to the website later. You can download them then and share the links more widely. And 2 short plugs before I start. The first of these is that we're actually organizing a workshop in London in the middle of May on the sort of topic that the seminar will also cover. So you're very much invited. There isn't a registration form you can register with yet, but we'll put that together in the coming weeks. So don't email us yet. We'll update you the moment that this is ready, and you can then register. And we'd love to have you and host you at UCL. And the second plug relates to something that Pierre and Camelia are setting up. They are currently putting together a track at AI Stats, whereby if you publish normally at statistics journals, but you would like to present at AI Stats in a poster session, you can actually submit to a track there and make that happen. Okay, so that's all the housekeeping for today. So I'll actually move on to the scientific part. And so today's talk I've called the Bayesian hangover, updating beliefs about updating beliefs. And I'll kind of do this in 3 parts. So I'll cover the hangover first and explain what I even mean by that. Right? It's not a scientific term, and it's obviously tongue-in-cheek. But really, what that first part is supposed to motivate is why we're here and why we care about post-Bayesian analysis in the first place. And the second part, I'll sort of move over to explain what I mean when I say post-Bayesian analysis, or at least some aspects of it. It is kind of impossible to cover everything because post-Bayesianism in itself is an inclusive term. It's not about defining yourself in opposition to other things. It's more about venturing beyond the confines of Bayesian inference. And so that's what I'll cover in the second part, and I'll put a lot of emphasis on three objects that I will speak about in more detail in the third chapter, the third part. And the third part actually is a short overview, a short survey of what we'll be seeing over the course of this first chapter. So I'll try to, relate the general themes to the speakers you will see over the next 6 slots of this seminar. Okay, so without further ado, let's start with the first part. So, when we say post-Bayesianism, or we say we want to sort of go beyond Bayes' theorem, it's important to say that at no point here will any of us advocate for the abandonment of Bayes' theorem. Bayes' theorem is a mathematical truth that tells you about the inversion of conditionals, and so we will not contest that. What we will contest is the translation of Bayes' theorem into an epistemological principle. So at the point where the mathematics hits the real world and where really you are talking about applied epistemology. Because in order to do this, what you need to do is you need to specify a kind of data model which tells you how you would describe the data you've seen for any given parameter. And then you need to formulate prior beliefs about that parameter space in order to obtain a Bayes posterior, which is just an inversion of these conditional probabilities, and which has many advantages, no doubt. 3 of these are that it averages over models rather than picking like one hypothesis in your hypothesis class, that it allows you to quantify uncertainty about the parameter that you're interested in directly, like by its very nature, and that it allows you to include domain expertise via the prior. And so overall, Bayesian inference has been and will remain a very successful mathematical toolkit for scientific analysis and data analysis more broadly. And there are many, many positive examples we could name. One of them, for example, is Gaussian process regression. I work a lot on Bayesian machine learning, so this is a very natural example for me to bring up, whereby I think it encapsulates a lot of what people love about Bayesian machine learning. So you observe data points more and more, and you see this red region here, which slowly collapses around a function from which these data points come as you observe more and more data points. And so you can see, we're averaging over a model. That's where the red region comes from. And at the same time, that averaging quantifies uncertainty about the parameter of interest. In this case, the parameter really is a function. So it's really an infinite dimensional parameter. And you can include your domain expertise about latent function in various ways in Gaussian process regression. All that being said, Bayesian inference, while it has been the pillar of a lot of scientific analysis, the pillars upon which Bayesian inference itself is built, they can be a bit fragile. And so this is really why people have started venturing beyond Bayesian inference. And so there are sort of 3 key assumptions you need to make. There are more assumptions, but I would say 3 assumptions that are most important and most fragile that have made Bayesian analysis sort of being questioned increasingly over the past few years. And the first of these is the assumption of correct model specification. So correct model specification simply means that in the parameter space that you have set up, there exists one element which can recover your true data generating process, so that the data can be adequately described in terms of at least one parameter in that space. And this is very important because it has a direct knock-on effect on how you should think about the priors, because priors are really meant for you to specify your beliefs about the true state of the world. But the only time when that is possible is actually when the true state of the world can be recovered by the parameter that you've set out to learn about. And then the other thing that you need to do when you specify prior is you really need to quantify your uncertainty about the true state of the world precisely. And we know that this is essentially not possible. If I ask you to write down your prior about the height of people in this Zoom link, you'll find it really difficult. And it's very unlikely that you write down, an exact Gaussian density if you actually think about what your true uncertainty is. And inherently, that's because humans don't really reason probabilistically. So some of the foundations of Bayesian inference are kind of really difficult to implement once you think about them very carefully. And then the third assumption relates to practicality, and I think it's probably the one that people are most familiar with, and that relates to essentially being able to compute the Bayes posterior. It's all fine and good to write down an version of probabilities, but unless you can actually compute the object that comes out of this, it's not really very useful. So these are 3 assumptions that have kind of become increasingly scrutinized and challenged by inferential practice. And they're the assumptions that often make Bayesian inference fragile in practice. And in order to convince you of this, I'll I'll spend the next few minutes walking you through a kind of worked example in form of a case study. And that case study relates to the Boston housing data set. And what I want to do here is contrast the way, the origin of Bayesian analysis, let's say, from trying to understand data in an experimental and scientific way to what we're actually often doing today, for example, in Bayesian machine learning. So in traditional statistical analysis, what you start out with is an expert that has a very clearly defined research question and very carefully collected data. And they formulate a model whose parameters actually they really care about, because these parameters tell them about the way of the world. It tells them about the truth of the world. That's ultimately what you're trying to model as a scientist. And so you carefully combine what you already know about whichever area of study it is you're engaged in, both in a likelihood model, which tells you where the data came from, and a prior, which extracts what's known in the field about the parameters that you are studying. And then you put that all together, and the only thing that's left for you to do is select a Markov chain Monte Carlo algorithm or other inference algorithm that allows you to, compute the inversion of these conditional probabilities. And actually, the Boston housing data set, which many of you may have encountered in sort of classical machine learning publications as a kind of benchmark data set, comes from this tradition of data analysis. So this is a data set that originates in the late 70s with two economists, I believe in Canada, who asked, what influence does air pollution have on housing prices in the city of Boston? And so when they set out to study this question, because it's a very carefully defined scientific question in their field of expertise, they write down a model. In this case, it's like a log linear model, but it's very carefully motivated by economic theory. So you can already see there's a lot of influence on the domain expertise coming into how you set up this model. And they're setting this up with very clearly distinguishing parameters they want to learn about, parameters they need to control for in order to not conflate their conclusions. And it's very easy to set up a prior for this kind of model because each of the parameters has a very clear meaning in the real world, or at least in the economic theory under which you operate. And computation actually isn't very difficult because it's a linear model. So it's quite simple to use most off-the-shelf Markov chain Monte Carlo algorithms. So this is a classical example of what Bayesian analysis was built to do and what it excels at. But this is actually really different from what we often do in Bayesian machine learning today. In particular, when you look at a standard Bayesian machine learning paper, normally there isn't a very clearly defined expert research question that you're trying to solve. Rather, it's about the algorithm itself. So normally the paper starts from some kind of flexible model and default prior, really, that you then apply to various different data sets to draw conclusions about what you can learn about that particular data set. And often the focus is also on prediction anyways. And when you do this, because the model is much more flexible, one of the immediate consequences is that that last step, inference, is much less off the shelf. It needs to be much more hand-tailored to the specific model class and prior class that you have actually set up. And this is the context in which we see the Boston housing data set today. So for example, I could have picked amongst a million different examples here, but I'm taking this paper from 2020 by Tim Pierce and colleagues, which is, I think, emblematic of the kind of thing we're looking at. And the research question is, in some sense, quite generically a machine learning research question, which is, does the algorithm that I'm proposing in this paper improve prediction on holdout data sets on various regression tasks, for example, the Boston housing data set? And so they do this by setting up, a neural network model here, which you could argue is a well-specified model in the sense that it can recover most data generating processes. But that's really where the good news ends, because by virtue of how you set things up, the parameters lose interpretability. So it's quite hard to really set up priors that are meaningful. Like the idea of handcrafting priors that you could do in sort of traditional Bayesian analysis breaks down. And in fact, what you need to do in this paper, in order to even hope to compute anything, is you need to work with Gaussian priors. So immediately you're extremely restricted with what your priors can even look like. And then you still don't know what those parameters mean. And then even though you've already compromised on what the prior can look like, you need to compromise further in terms of the computations, because anything you can do here is really a very, very coarse approximation to the actual inversion of conditionals that you ought to be doing under Bayesian machine learning. So we see that we have two completely different approaches to data analysis. And this is not to say that one of them is bad, by the way. This is just to say they're founded on completely different principles, different epistemological principles. And while Bayesian inference can tell us a lot about one of them, it's perhaps not true that it can tell us a lot about the other. And so what this basically means is the assumptions that we have created in Bayesian inference for historic reasons, they work really well on one of these, and they are quite fragile in relation to the other. And this is really the origin, as far as I can tell, for what I've called post-Bayesian approaches here, which really have one common theme, and that theme is how can we keep the benefits of Bayesianism without relying on assumptions that ultimately render our algorithms and methods fragile. And so this seminar really is an attempt at organizing the community of people that work on these questions under a common banner. And so in light of this, post-Bayesianism is explicitly not meant as something that's exclusive. It's explicitly meant as something that is inclusive. And so, we'll talk about several recipes for post-Bayesian approaches, but that doesn't mean that the only ones in existence that people have thought about. Okay, I think this is a natural point to take any questions if there are any. Jan and Matthias, I'll give you like a few seconds. Okay, I think we're moving on, but I can see Matthias shaking his head. Okay, so we're moving on to the second part. So having motivated why we are here today and why we care about post-Bayesian analysis, I'll walk you through some of the approaches that people have proposed, that I'm calling aspirin here, but that are geared towards solving at least some of these concerns and issues that we have run into. And I like to do this by means of a picture. So this picture is obviously schematic. It's, this is not a technically rigorous picture if you so wish. But imagine the space of possible belief updates. You have a prior and you have some data and you want to update your beliefs about some parameters. Then you can think of the base posterior as one element in the space of possible belief updates. And it's a belief update which relies on these three assumptions that we have just outlined and criticized at length. And so one of the first things you can do, if you think about the space, you can write it down more formally. You can say, well, my belief updates, they're really a mapping from the space of priors and the data space into the space of posteriors, which is actually the same space as the space of priors. And you can do this. It's not sure this is very helpful, but perhaps it helps you understand what I mean with this set of possible belief updates. And so the first thing people did really, once they realized that the base posterior only gets them so far, is they did something fairly simple, but as it turns out, rather effective, and something that we're still doing research on these days, and that's the power posterior. It's also sometimes called the cold posterior or the fractional posterior. It has many names, but the idea is always the same. Tempered posterior, I think, is another one. The idea is always the same. You take the likelihood, which is misspecified, and so you're worried about it sort of being miscalibrated against something like outliers, and you temper it. So the idea is that something that has, thin tails gets fatter tails by tempering it. It's a very simple approach, and it leads to this kind of object here, which I will probably just call the power posterior throughout the rest of the presentation. And the idea is that this can address certain types of model misspecification. This is a very old idea, and one of the first people to propose it is Peter Grunwald in his series of safe Bayes papers in the early 2010s. Which we'll get back to later. But what we'll also see later is that actually this is something that's most interesting in the small data setting. If you have a lot of data, the kind of robustness this buys you doesn't get you very far. And it only gives you one parameter to play with. So it's quite a restricted way of expanding our set of belief updates. And so very briefly afterwards, people started thinking more broadly. And the first thing they stumbled over afterwards is sort of the most natural thing you can think about. And that's formulating things in terms of quasi-likelihoods. I should clarify, I don't like the term quasi-likelihood because a quasi-likelihood has nothing to do with a likelihood. And in particular, you can see this by observing that a quasi-likelihood, which I should mention is an exponentiated negative loss. If you integrate an exponentiated negative loss, A, it doesn't integrate to 1, and B, it need not even integrate. This need not be an integrable function. So it's really a completely different object. But sometimes people find it helpful to think about these in terms of quasi-likelihoods. So all you're doing here is you're now replacing a likelihood function with an exponentiated negative loss. And by doing so, you obtain something that is, sometimes called the Gibbs posterior. It's a generalized posterior, the pseudo-posterior, quasi-posterior. Again, it has many names in many places. And again, so I'm referencing Posterior, Holmes, and Walker here, who I would credit with really proposing this as a general framework for learning from data. But again, this is not an object that was invented in that paper. Obviously, it's a much more ancient object. The Gibbs posterior is named after Gibbs, who's clearly been alive since much earlier than 2016. But anyway, so this object gives you a much broader range of addressing robustness, and we'll revisit that later as well. And this robustness will hold even if you observe more and more data. It's a much more stable form of robustness in some sense. You can generalize this further, if you will, and that's something we proposed in the early 2020s. And again, this representation here is a representation of the Gibbs measure and other posteriors as a form of optimization problem that trades off a data fitting term and a prior regularization term. And again, it's not something we invented. You can go back into the PAC-Bayes literature and even further. The Donsker-Varden theorem is, I think, normally credited to the 70s. So this sort of optimization-centric understanding of what a posterior actually does, much more ancient, but the idea of using it as an inferential device is a younger idea. And so here the idea is sort of just to generalize the Gibbs posterior further and see really which limits you can hit. And then there's one last idea that I'll mention, and it's interestingly quite orthogonal to all these approaches that I've listed here, and that's actually resampling-based or martingale posteriors. And interestingly, they don't really relate to all these other approaches. They do recover the base posterior, as do all these other approaches as a special case, but that's kind of one of the only points we know of where they meet. They might meet in other points, but this is actually not a well understood thing. And so this is quite interesting because we have here completely different generalizations that cover a completely different space of possible belief updates. And this is also something that's reflected in how we structured the seminar, because so the second chapter after we talk about generalized based is one that Edwin will lead, and that will focus exclusively on these resampling-based and martingale-focused approaches. And the third chapter that Pierre will lead focus on these PAC-Bayesian ideas, which relate a lot to representing things in terms of an optimization problem. And one of the natural outgrowths of framing things as an optimization problem happens to be the Gibbs posterior, but there were also other outgrowths. And in this first chapter, when we look at generalized space, we will focus mostly on these Gibbs posteriors and fractional posteriors, but we'll every now and so often link it back to an optimization-centric posterior perspective, in particular in Chris's talk in the fourth slot, I think. Okay, so in terms of what will be covered, so today I'm giving you a brief introduction into post-Bayesian ideas more broadly and generalized Bayes more specifically. And then in 2 weeks' time, we'll have the pleasure of listening to David Fraser, who's going to talk about essentially the toolkit we need to actually studying these objects. So this will be a lot of, the statistical and mathematical theory underlying a lot of the results that we have managed to obtain over the last few years. So that's really something to look forward to. It's sort of like a condensed way of looking at the tools that we've managed to create for ourselves to work with these objects. And then once we have that in place, Ryan Martin is going to speak about learning rate selection and the power posterior. So in this power posterior, we have this lambda, and this lambda actually is a really tricky thing to select. And Ryan has thought about this quite a lot, and he'll share his expertise on this with us. And the week after that, or not the week after that, 2 weeks after that, Chris will talk to us, and Chris will actually take this optimization-centric approach and speak about how we can refactor that slightly to make it what I would call prediction-centric. So caring about parameters insofar as they help us make better predictions, which is quite a novel development and quite interesting. And then after that, David Dunson will talk about the relationship between what's called coarsened Bayes, where you condition on a neighborhood of the data rather than the data itself, and how that relates to power posteriors. And Chris Holmes will end the chapter, and will also sort of hopefully shape an arc from these kind of approaches, these generalized based approaches, to the next chapter, because Chris has been involved in both of these ideas, and sort of take us through the trajectory of generalized based to martingale posteriors. Okay. Before I go on to the last part, where I'm just covering some basics on the objects we're studying in the first chapter, are there any questions we want to take at this point?
Yeah, we have one question from Dan Roy. I don't know if you would like to ask it, Dan. Otherwise, I'll go ahead.
Yeah, sure. Thanks.
Sure.
Yeah. So on your slide, you're talking about Gibbs and generalized and pseudo posteriors, and then the optimization perspective, and you're using this you're making this distinction between these Gibbs posteriors, say, arising in a PAC-Bayesian or other contexts, like, for example, this optimization variational principle shows up all the time in finance, for example, with its use as a inferential, I forget the other word you use, some inferential something.
Probably device or something.
Yeah, inferential device. Yeah. So the basic question is, what is inference meaning here to you? And to allows you kind of notice a difference in how these objects have been used in the past and how you hope to use them.
Yeah, so okay, this is a very small question to start with, Dan. Thanks. Yes, I think what I was trying to get at by my remark, which perhaps I could have phrased more carefully, is that when you look at Gibbs measures, for example, in PAC-Bayes, right? Let's take PAC-Bayes as an example, because I have at least rudimentary knowledge. I'm not an expert in finance. But when you look at PAC-Bayes, normally the Gibbs measure pops up as it just happens to be the minimizer of a particular risk bound. And it then enables you to say, when I randomize my estimator in a particular way, I get a generalization bound. You don't actually care about if we want to call that uncertainty represented in that object, other than the fact that it gives you a better randomized estimator. So where I would draw the distinction, and I agree it's a difficult distinction to draw because we still care about these properties as well when we think about it as an inferential device. But there are other aspects that we would care about when we study the Gibbs measure in its own right that aren't so interesting if you think about PAC-Bayesian analysis. So one of those I will cover in a bit relates to robustness of these Gibbs measures. So you could be interested, if you think about them as an inferential device, so you want to learn about the parameter, and the parameter itself is meaningful, not only the prediction that's implied by randomizing over the estimator from that Gibbs measure. If you actually care about the uncertainty in the parameter itself, and you're, for example, worried about something like outliers in your data set, there are ways in which you can design these Gibbs measures so that they are robust in a Huber sense. And so that's not something that, for example, you would care about in PAC-Bayes. So I'm not sure that answered your question fully, but I think the distinction between using it as an inferential device and PAC-Bayes is necessarily not a super well-defined one, because actually we often use PAC-Bayesian tools to analyze these Gibbs measures anyways. So even when we study these other statistical questions, we'll have to rely on PAC-Bayes because it's thought so much about how we should conceive of these objects in the first place. Does that answer some of your questions?
Yeah, I think this will be an interesting question to return to, I think, and sharpen our answers to.
I agree. Thanks, Dan. Are there any other questions, Jan? No. Okay, great. Okay, so yes, in this third part, we'll kind of briefly visit these three objects and introduce them insofar as it's appropriate at this point. Obviously, we'll have other speakers dwelling on them in much more detail. So starting with this power posterior, like the first question you could really ask is, what does this actually do if you've never seen this object before? Immediately, you're obviously thinking, oh, if I raise this to the power and this power is, let's say, smaller than 1, I should expect that there's a kind of quasi-likelihood that is more heavy-tailed. And conversely, if I'm raising the power to something that is larger than 1, I should be sharpening the likelihood. And this is essentially what happens. So I've stolen this picture here from one of the papers from Aki Vatari's group. And what you can see here is for different values of this lambda, you can see the same likelihood and the same prior and how they behave with relationship to one another. And one of the things you can see is that basically the posterior becomes a less pointed object as lambda decreases and a more pointed object as it increases. And you can also see that the lambda serves the function of trading off the prior against the data. So as you decrease lambda, your posterior will look closer to the prior, which is kind of obvious. And this should also immediately point you to one of the limitations of using this for robustness, and that is when your prior is actually not a very good prior. If you are forcing your posterior to be more like your prior, this is not actually, well, it's robust in a strict sense, but it's not necessarily the kind of robustness you want. Okay, so perhaps the more interesting question to ask with these objects is why would you do it, or why should we do it? So this is an example taken from Peter Grunwald and Tim van Ommen's paper at Bayesian Analysis 2017. Don't worry, I'll put it on the slide in a second. But it's essentially a linear regression model that you're fitting to some misspecified data. So we have 50 parameters here, so the red D that you're seeing there. And we have a variable number of observations. And what we're plotting is the kind of risk we get out of doing inference on these parameters in different ways. And you can see they're kind of like two regimes, roughly. There's like a large n regime and a small n regime. And really, when I say large n, I mean n relative to the number of parameters here. So when n is small relative to the number of parameters you're trying to learn about, you can see there's a kind of weird spike of this green and brown line. But then as n increases further, you can see that all these lines behave vaguely similarly. So what are these two spikes up there? Actually, it turns out they're exactly the base posterior and the maximum a posteriori. And so what this tells you is that in small n, you can actually lose a lot in terms of squared risk when you use Bayesian analysis in a misspecified model. And one of the things that was proposed and that Peter was instrumental in proposing is choosing a value for this power in the power posterior to eliminate this effect. And you can see this quite nicely that for the small n case, you eliminate this effect. And for the large n case, it doesn't really matter so much anyways. And so that gives you the answer why you would want to do this. It basically gives you better risk properties or predictions if you're in a small sample setting. And there are obviously many other things we've discovered about these objects, and I will not dwell on them much. I will briefly mention them and relate them to what we're going to hear over the coming months. So for example, one thing that is quite interesting is we have found that these power posteriors, as well as their variational approximations, they actually concentrate in a nice way in many situations where the standard base posterior would not concentrate, or at least we can't prove its concentration. And David will talk next time about asymptotics, which ties into this sort of broader area of discovery. And this is really one of the things that put these objects on the map at first in the early 2020s, I would say. Or I wouldn't say first put them on the map, but renewed interest in them is perhaps the fairer way of expressing that. The other thing we discussed already and that we discovered in using these objects is that actually it's quite difficult to choose this lambda. So don't be misled by this example I showed you, this really nice example. Actually, the computations you need to perform to choose this lambda if you're using Peter's approach, they can be computationally quite cumbersome and it can take quite a long time to run them, rendering ultimately a question whether you should really bother with them. And so people have studied whether it's really the only way that we should choose lambda. Maybe there are other ways and which is the best way. And that's not a question we have an easy answer to. And so Ryan will walk us through some of these aspects in his talk. And then the other thing that you've seen already in the last slide is that actually when you're in the large n regime, this robustness property actually vanishes very quickly. We have a paper that we published recently on this phenomenon. And there's another paper from 2 years ago published at JMLR, which showed that the same is true essentially for the robustness effect, which is kind of unsurprising. As you get more and more data, the base posterior reverts back to the log likelihood minimizer. And this is true regardless of the lambda weight that you've chosen. And so based on this insight, Chris will talk a bit more about what you can actually do even for large n if you care about predictive properties of your posteriors. And the other thing that is kind of well known about these power posteriors is that they can actually be understood as an approximation to what is called a quiescent posterior. So a quiescent posterior conditions on the neighborhood of the data, and at a particular limit, you recover these power posteriors. And David will speak about this in his talk. Okay, what's interesting about this tapestry that I'm showing you here is actually, when we think about positives and negatives, actually the entire right-hand side of this slide is sort of negative properties of these power posteriors. They're kind of difficult to deal with sometimes because it's not easy to tune this hyperparameter. And actually, if you have enough data points, a lot of their perceived benefits become obsolete and kind of vanish. And this has motivated people to study these Gibbs posteriors in a bit more detail. And so to just give you an example and perhaps brighten things up with a nice moving figure, you can see why these Gibbs posteriors have become popular. So on the left here, we see basically a standard Kalman filter, which you can think of as a Bayesian update. And the same result you see on the left would be true if you use the power posterior here as well. And basically what we're seeing is there is an attempt to filter. So there's this Kalman filter actually struggles with this whenever there are a couple of outliers, and it takes quite a long time to find its way back to the true latent function here. And you can contrast this with a particular Gibbs posterior on the right-hand side. Details aren't so important, but what is important that actually this object on the right-hand side also has closed form updates, much like the standard Kalman filter. So these compute in the same amount of time. It's not like you have to waste a lot of computational effort on the right-hand side. But what you can see is when you base your updates on a robust Gibbs posterior, you do trace out these latent functions much more closely, and you actually perform much, much better. And so really the motivation for a lot of these Gibbs posteriors is robustness to model misspecification. And so one short note here, in this presentation, I'm writing Gibbs posteriors as though they're always dependent on a statistical model. This isn't true. Everything I'm saying could be true for any arbitrary parameter. The parameter need not refer to the parameterization of a particular likelihood model. But I find that most of the interesting advancements we have made, at least in this field, relating to Gibbs measures, take the form where the loss actually relates to a likelihood model. So I'm going to take that liberty throughout the rest of the presentation. One of the first questions we can ask if we see this Gibbs posterior is how to think about this. And obviously one answer to that question is via PAC-Bayes. But if you're not thinking through the lens of PAC-Bayes, which we're not doing in this chapter, and so that's something we'll defer to the third chapter, then one way we can think about it is in terms of general Bayes updates. And so to see this is an idea that's articulated in Basirio, Holmes, and Walker's seminal paper from 2016. When you see the normal way that we update Bayes posteriors, right? The what's the phrase? Today's posterior is tomorrow's prior, I believe is the phrase. When you follow this adage, you can see, if your data is modeled as IID at least, then you can actually update the posterior after n observations by taking the posterior after n-1 observations and essentially adding one likelihood term. And so the question asked in this paper is essentially, when can we extend this further? And the answer is actually whenever your losses are summable. So when your losses are summable, so they decompose over the observations, you can essentially endow a Gibbs posterior with the exact same updating principle. And so you can think of a Gibbs measure as a general Bayes update. So obviously the main restriction of this, right, is that you need the losses to be summable. But you don't actually you don't need to rely on losses to be summable to work with Gibbs posteriors. That's because we can think of them in general, in more general sense, as this optimization-centric object, where we're trying to trade off a data fitting term against a regularization term, where that regularization term depends on some kind of prior. And here, in terms of notation, the calligraphy p theta is just the space of all probability distributions over theta. Okay. Yeah, so that solves this problem. And as I've mentioned a couple of times now, but the role of PAC-Bayes is basically to figure out what choices we can use for both this prior regularizer and the data fitting term to give us some good generalization guarantees after we mix over this Gibbs measure. And there are other questions. So this relates back to discussion with Dan earlier. There are other questions that are not asked by PAC-Bayes. One of them is what happens asymptotically with these Gibbs measures, and that's something that David's going to speak about next time. And there are also other questions relating to the innate properties of these Gibbs measures as inferential devices, as we called them earlier. And the two questions I want to briefly talk about now is, when is this Gibbs posterior actually robust? And robust here, I mean in the Huber sense, so robust against contamination and outliers. And the second question that follows straight from that first question is how we should design losses that give rise to these robust Gibbs measures. Okay, so the setting here for robust Gibbs measures is essentially you have some data generating distribution, which is this Q epsilon, and it's composed of two parts. It's epsilon times C, where the C is some arbitrary contamination distribution, and it's 1 minus epsilon times Q0, where Q0 is what you're really trying to learn about, and it's also part of the data generating mechanism you can actually model with your model class. When you think about this in terms of a picture, you can think about it like this. So you have some kind of histogram here where you have a contaminant that kind of doesn't fit, let's say a Gaussian. You're trying to fit a Gaussian to the data. You have a contaminant that doesn't fit a Gaussian. What you would really want to model is the bulk of the data minus that contamination. But if you just apply a standard Bayesian technique and try to fit this entire histogram, you will oversmooth to that contamination. A different way of writing this down is in terms of algebra. So you could say, well, whether I sample my data from Q epsilon or I sample it from Q0, I want that the Gibbs posterior I compute at the end roughly looks the same. This is the kind of robustness we care about. And so when we do this, we can basically say what I need here is some level of distance between Gibbs measures. And then I want that distance to be bounded, and I want it to be at most linear in the size of that contamination. That's sort of my benchmark for robustness. And again, this goes back to sort of classical statistical robustness of the Huber variety. The first thing you need to define is actually this distance itself. And it turns out that what's really convenient here is the supremum distance. So you're just looking at the densities with and without contaminated data, and you're looking at when they are furthest apart. And this is the thing you want to bound. The second thing you do is you take a supremum over a set of possible contaminations. Because if we go back one slide, so if we just look at the right-hand side here, the constant in C could in principle grow with C. So you could just make the contamination arbitrarily poor for this bound to become vacuous. So you really need the guarantee of this form where you're taking a look at both the worst case in terms of where the posteriors are most apart from one another, but also worst case in terms of the nature of the contamination. And then you still want things to only be linear in the size of the contamination. And when you take this view and this perspective on the problem, you can actually identify a key quantity. So this is something we did with Takuo, FX, and Chris in the JSSP paper in 2022. And the key quantity really is the limit of what I've just written down here. So what I've just written down here is the scaled difference between the contaminated and uncontaminated loss, and you scale it with the size of the contamination. And then you take the size of the contamination to 0, which means you end up with the derivative evaluated at 0. And essentially what you find is that you need to be able to look at this sensitivity of the loss, let's call it. You need to look at the sensitivity of the loss, and you need to be able to bound that sensitivity across the entire parameter space to make sure that nowhere in the parameter space does the loss escape to infinity as you add a tiny amount of contamination into your data. And if that's the case, you can call the loss robust. And if the loss is robust in this way, then you can actually show that the posterior is also robust, roughly speaking, okay? And so the answer to the question when the Gibbs posterior is robust, perhaps unsurprisingly, is it's robust whenever, you know, the loss itself is also robust. And one thing to remark upon here that sort of ties everything back to the Bayes posterior, which you can recover as a special case of the Gibbs measure for the negative log likelihood as the loss, is that in general, this key quantity is not bounded for log likelihoods. There are certain likelihood functions where this is bounded, but in general, there's not a guarantee that this is true. And there are other ways of obtaining losses where this is always true, regardless of your likelihood model. And that's the next question we look at. Like, how do we design losses where regardless of the likelihood model I put in, the loss actually has this nice robustness property? And there's a long list of literature I've given here at the top, because this kind of general recipe I'm outlining here is something that's been done in this literature over and over. And the general recipe is this. When you compute the standard Bayes posterior, you are actually using a loss that approximates the Kullback-Leibler divergence between the data generating process and your model. And we know that the Kullback-Leibler divergence is not robust to model misspecification. So you can reverse engineer this by choosing a discrepancy that is robust. And then if you can approximate that with some kind of loss, you have a robust loss. And for example, this is what you do when you use what's called MMD Bayes, where you use the maximum mean discrepancy as the loss. It's true for alpha, beta, and gamma divergences. And it's also true for Stein discrepancies and the weighted Fisher distances that we've seen in the more recent past. And so very, very briefly, coming back to how we can relate the Gibbs measure to this optimization-centric perspective. When we look at this here, you know, there are 3 knobs we can basically tune that give us access to 3 different extensions to this idea. So one of them is we can change the space over which we solve this problem, and we're basically ending up with variational inference. We can change what the loss actually refers to. So normally it's a data fitting term, but we could produce something that is much closer to a predictive term. Again, that's something that Chris will look at. Or we can change the way we regularize against the prior and hopefully embed some kind of robustness against prior specification. There's lots of papers that have done versions of this. And Chris will speak about one of these that is, I think, one of the most interesting ways of going about this. But whichever way you go about working with this object, you now actually have to deal with something that in general is really hard to compute. And so obviously, one way of computing it or approximating it is actually doing variational inference or generalized variational inference, where you look at a set of parameterized distributions and you just solve the problem over those. But then actually for certain choices of losses and divergences, there is something more interesting you can do. And that essentially amounts to an infinite dimensional version of gradient descent or Wasserstein gradient flow, where you choose this set of measures to be the set of probability distributions with finite second moment. And when you do this, you can now actually generate something like a sampling algorithm that can target a measure which we know is unique and we know it's defined, but we don't know what it looks like, which is, to the best of my knowledge, at least, it's sort of the first sampler of its kind of that form, where you know the posterior you're trying to target exists, but you know what it looks like, and you can still sample from it. And it also tells us a short morality tale. And on that morality tale, I'm also going to end today's talk. So what's that morality tale? So if we look at this optimization problem, one easy and simple instantiation of it that we all understand is when we plug in the negative log likelihood and we integrate that over Q, and we add the KL regularizer, because in that case, the target that this thing targets is just the base posterior or the cold posterior. And you can run the Wasserstein gradient flow. You can run this infinite dimensional optimization problem on that objective. And when you do this, you can actually show it just amounts to the Langevin diffusion. And we know from years and years of research on Markov chain Monte Carlo that the Langevin diffusion, converges to a well-identified and defined density. And in particular, that density is actually, the power posterior or the base posterior itself. And so it's a very well understood algorithm, and it just happens to be recovered by this infinite dimensional gradient descent or Wasserstein gradient flow on this objective. But what happens if we push this lambda from the power posterior all the way to infinity? Okay, so we're basically eliminating this divergence. What happens is you are now performing Wasserstein gradient flow on a linear objective where you're just looking at the expectation of the negative log likelihood. And this is basically a deep ensemble. So now the Wasserstein gradient flow recovers a completely different algorithm. This algorithm converges to what I would consider an ill-defined discrete measure. Discrete is obvious. It sort of ends up in the local minima. Ill-defined, what I mean by that is that it completely depends on where you initialize your Wasserstein gradient flow. So wherever you initialize, you basically crush it into the nearest local minimum. Okay, why do I bring this up? I bring this up because clearly these two algorithms, even though they both are recovered as a special case of this objective, they're actually completely different, and they shouldn't be treated as being the same object. And yet, oftentimes in the literature, they are actually claimed to be the same thing. Right? There's a fairly persistent claim in the Bayesian machine learning literature that deep ensembles are performing a way of Bayesian inference, which is not correct. I mean, if you think about what the algorithms are targeting, again, one of them is a continuous density and it has a prior in it. The other one has lost the prior and it's a completely discrete measure. These two objects are distinct. Now, this is not to say, this is not trying to bash anyone's work. I think this is great for us as a community, that these misunderstandings exist, because they really motivate why the work we're doing in the seminar and in our spare time and for our work, why it matters. Because what we see from this is that in practice, the orthodox Bayesianism that you were taught about in school has already been abandoned by practitioners anyways. Like the base posterior is this very nice property. It comes from scientific analysis. You use a prior. The prior has a very specific meaning. But a deep ensemble doesn't even have a prior. It's a discrete measure. It's not continuous with respect to the prior. Completely different objects, but we're using the same terminology. And the fact that we're using the same terminology, or at least in Bayesian machine learning, people use the same terminology, tells you that practitioners often don't realize how different these objects are and how distinct really you can think about uncertainty quantification. And not everything that performs uncertainty quantification is necessarily Bayesian in some way. And if we don't pay attention to the ramifications of these important differences, then we can make incorrect claims, such as deep ensembles are Bayesian. But more importantly, it is not just about semantics. You can draw false conclusions, or you can think you're safe with the conclusions you have drawn because it's Bayesian after all, and Bayesian is some sort of guarantee, when really that's not the case. And so that in turn, I think motivates me, and I hope motivates you to help people and to provide, first off, acknowledge that post-Bayesian methods are already being used and they're not going away. And then also to help and develop clear formalisms that allow people to build on what they already have and understand better the kind of uncertainty they get out of them and what kind of design principles would be needed. Because it's my hope that we can, maintain Bayesian and generalized Bayesian forms of inference into the next century. And we are only going to do this if we help the ideas that we already have and that have already proven so powerful to evolve further and to adapt of the challenges that we're facing now. Anyways, and with that, I'll leave it for today. And we have, I think, about 10 minutes left for any questions, if there are any. Thank you very much for your attention again and for the mass attendance. It's great that so many people are interested in this, and I hope that we'll maintain momentum and that we'll all see you over the coming months. And I'll hand off the question and answering duties to Jan and Matthias.
Yeah, brilliant. We've got a few in the Q&A, which are quite nice. Should we start off with David? David, I don't know if you would like to ask it yourself, otherwise I'll go ahead.
Yeah, I know. Happy to. Hi, thanks, Jeremias. Really nice talk. Thank you so much also for organizing this workshop to all of you. Sorry, the lecture series, I guess. But I'm just curious. Uh, I mean, it obviously there's a lot of compelling reasons to sort of try to make Bayesian inference more robust, and then sort of especially in the context of having misspecified data generating processes. But there seems to be an obvious, or like to me intuitively, there's an obvious trade-off where you're sort of saying, okay, my data contains less information about the process that I'm trying to model, or sort of, or at least you're taking away some of the injective bias from knowing the data generating process. So I'm just wondering, sort of, have you sort of studied sort of this information loss, and can we quantify this in a systematic way across problems?
I'm not sure I understand the question. So what do you mean information loss?
So, okay, let's, in the ideal setting, we know sort of we have the data generating model structure, and then we can define price. And so now we do Bayesian inference, we get our posterior distribution. So now we keep that same setting, and now we replace this robust inference approach rather than using the sort of the classical Bayes. So what I would expect is that the posterior distributions are probably inflated, sort of wider than before, and I would call this information loss. So I'm just wondering, sort of, is this something that you've thought about before, and something to consider?
So yeah, so okay, so there are two things I think to say. So the first is that it's not always the case that these generalized Bayes posteriors are more inflated. So if you raise a likelihood to a power, yes, then you can show this. But in general, if you use a completely different loss function, they no longer operate on the scale of a likelihood. So one thing that I've glossed over in this presentation, but that's kind of really important, is that you don't get rid of choosing this lambda parameter, even if you choose a general loss, for this precise reason. Because what you want, ideally, is some sort of more vagueness in your posterior conclusions relative to what the Bayes posterior would give you if you suspect misspecification. But it's not actually something that happens automatically. So you need to carefully tune these lambda parameters. Now, in terms of, I guess it's like a loss of efficiency that you're talking about. But statistical efficiency really only makes sense if the model is well specified. So the only way you could study your question is if you say, my model isn't well specified and I'm using a Gibbs measure. And then the way to think about this is to look at the easiest way to study this, I think, would be to look at the asymptotic variances. So you often, and David will talk about this next week, you can often study how these objects behave in the limit, and it gives you like some, like if the model is correctly specified, you basically want the asymptotic variance that the Bayes posterior gives you, but this is no longer true under misspecification. But let's assume the model is well specified. Then you could say, well, if I'm mistakenly using a robust method, this is how much I'm losing in terms of the variance. So if you're just caring about one parameter, you could just look at the ratio of the variances in that case. But I don't think this has been studied. No.
Mm-hmm. Okay, but thank you.
Thank you.
We have two more questions about the power posterior, so maybe I'll try and combine them into one. So one from Andreas is on lambda as an integer would tell us how we repeat the data, so increasing it gets us closer to the MLE. And another one asking whether powers less than one are still helpful if the data, no, sorry, my bad, if the parameters are not IID, but have some Markov properties which are not models.
I'm not sure I understand the second question. If the parameters are not IID.
Oh, sorry, no, the observations are not IID given the parameters.
Oh, I see. Okay. So the first question, if lambda is an integer, you're getting closer to the MLE. This interpretation in my mind is correct. So when you look at the optimization centric version of writing a power posterior, if your lambda is a 2, you're basically double counting your data. If it's 3, you're triple counting it, and so on. So I think this is the right way of thinking about it. And obviously, as lambda goes to infinity, indeed, you're recovering the MLE if it exists. So that I agree with. Can you repeat the second question, Jan?
Yes, I can. Although maybe the person who asked it would like to ask it themselves.
That might be easier.
Thanks a lot. Yeah. So what I'm asking is, I've used power posteriors in order to reduce confidence. And this is particularly effective when the model is somehow naive in the sense that you're not capturing some, let's say, inter-observation correlations that exist, right? So essentially, you are inflating a lot. You are making, let's say, overconfident estimations about the parameters. essentially, right? Because you essentially you are considering you have n observations, but they are correlated. So essentially you have n divided by something, or times lambda, or lambda less than 1. So it's a way of reduce confidence this way, right? So I've seen that a lot, being a lot very helpful in these scenarios, right? Yeah. So this
that makes
it's
sense.
again a model modification, right? But it's a very particular one. Like you're not taking considering the correlations that exist in your data, right? Yeah, that's what I want to point out.
Yes, okay, that makes sense. I don't know how much theory there's been done on this case. I've not come across it. Maybe it exists. If it does, I'd be interested in that. So if someone knows of theory in that realm, I'd be interested in reading that. But it seems sensible to me that they would do that. Yeah.
One from Owen, which is about what do you find the mainstream Bayesian's main source of skepticism to be when you are trying to convince them of post-Bayesianism?
Oh, there's shades of this. So I think normally that the main obstacle is this depends a bit. So it depends whether you talk about a theoretician or a practitioner. But a lot of theoreticians that I talk to, I think their main apprehension is that they fundamentally don't care what practitioners are doing. And so when you tell them about all of this, one response that I have gotten on several occasions is, well, people should just specify their priors and their likelihoods properly, which I agree with. If you want to do Bayesian inference, that would be great. But the point, obviously, of this work is that that's not really an option. Otherwise, you wouldn't be doing this. And there's obviously lots of problems where you shouldn't touch any of this advanced machinery, and you should just stick with the Bayes posterior because it's the perfect tool for the job. So that's one apprehension I have often gotten. Another one, and there are many open questions, right? This is a big Swiss cheese, this field. I mean, there's many things we don't understand. And one very good criticism and pushback I often get, to which I don't have a satisfying answer, is what does the uncertainty really mean that you're getting out of this procedure? And I think it's a good question. It's some form of subjective uncertainty about the parameter, but it's not a conditional probability in the sense of a Bayes posterior, right? So the validity of the answer I normally give to this is, while this is true, the Bayes posterior under misspecification gives you a conditional probability that is itself not informative because it's based on wrong objects. So you can multiply the conditional and the prior together and invert them, but they don't mean epistemologically what you would like them to mean. So even though I don't really know how to interpret the uncertainty of the objects that I'm working with, I contest that the same is true of the Bayes posterior the moment your model is misspecified. So it's kind of, I think, the common theme of a lot of these tends to be that people are very married to the very neat assumptions we impose when we do Bayesian inference. And it's kind of uncomfortable to think about what actually happens to all the pretty math that you have when they fall away. And a lot of the math we have to work with in these generalized Bayes procedures is much uglier than what you have under the sort of standard assumption with Bayes posteriors. This is one of the main apprehensions I encounter often. Okay, so I think we're over time. So let's leave it there. But thank you everybody for attending. It's been a real pleasure to have you all, and hopefully we'll see you again in 2 weeks' time when David speaks about the asymptotic theory. Thank you.